Hello and welcome to another lecture of ECE 205. So let's jump into it. So for this lecture, we really have one goal. We want to extend what we've done before to solve differential equations of this form here. Okay, so recall previously, I didn't have this cosine and sine term. I just had either a polynomial on its own or an exponential times some polynomial. Okay, so here again, A, B, C, these are going to be constants. This new omega and the new lambda are going to also be constants. I'm going to assume that A is non-zero, otherwise we have a first order differential equation and things don't apply, and we know how to work in that case. And further, we're going to assume that omega is non-zero, because if omega was 0, then all of this stuff here simplifies to simply this polynomial p of x, since cos of 0 is 1 and sine of 0 is 0. And then this would be of the form p of x e to the lambda x, which we've seen before. Okay, so again, it's a direct extension of what we've done before, and we're going to kind of follow the same idea here. So in particular, to solve these differential equations, we're going to extend our method of guessing to try to form the solution from there. Again, this method is also going to be called the method of undetermined coefficients, since the polynomials that we'll end up guessing the form of have coefficients that we don't know their values. Okay, and let's look at some constructive examples of different cases that you could potentially have, and at the end, we'll generalize this to a kind of nice theorem. Okay, so another example-heavy as opposed to theory-heavy lecture, which probably helps to break the dense theory stuff up. Okay, so first we want to find a particular solution of this differential equation. So let's check this out. Okay, so if I look at this, the natural kind of first thing you might guess or want to do is try to guess at what the form of an equation is. So previously, when I was dealing with exponential forcing terms over here, I made a guess of the form of, say, if e to the lambda x was the forcing term over here with some constant, I would make a guess of the form, say, this or some constant times it, or potentially some arbitrary function times it if I had a polynomial sitting here. Okay, so in this case, since I just have these sines and cosines, and I know that sometimes sine of 2x could be a solution to an equation of, well, the complementary equation for this type of a differential equation, it's natural to look for a solution to this particular, or a particular solution to this differential equation by simply looking for a solution, y sub p, that's going to be of the form some function u times, here my cosine of 2x, and let's call this u1, plus another function u2 times sine of 2x. So note, this ansatz doesn't actually restrict anything, because u1 could be something divided by cos of 2x, so it could literally be any function you want here, right? So now, in general, this method will always work as a kind of way of deriving a new equation or new equations for u1 and u2 that could solve this differential equation, but it very well could be the case that I can assume something more particular. So I could assume this. So this is something that I could do, but it turns out that here, since these are constants, and we'll kind of see with more examples kind of how this works in more general cases, but since these are constants, I can assume these u functions here are just some constants c1 and c2. Okay, so in general, we could use this method, but let's just try this where u1 and u2 are just constants, just to see what happens. Okay, so cleaning that up a bit, we get this thing here. Okay, so again, this is my assumption, so if I want to actually test it, I need to compute its first and second derivative and plug them in. So just very quickly doing that. Okay, so from here I can say thus this equation, my y double prime minus 2y prime plus y, here if I take this and plug in my y sub p, what do I get? Well, the first term will simply be this guy here, so we'll just copy him and throw him down here. Then to this, I would subtract a 2 times this term here. And then to this, I'm just going to do the next one on the bottom row here. Here I would have a plus, and then just parentheses this. Okay, so just cleaning it up a little bit, that's what I get here. And here I can simplify this whole expression just by noticing that I have some cosine terms and some sine terms here. Okay, so just kind of a pro tip here. We can simply note that the cosine terms will have the C1 from here, nothing from this term. Over here, we're going to get a minus 4C2, and then we're going to get a minus 4C1. So if we put all this together, I'm going to have a minus 3C1 minus 4C2. All of this will be multiplied by my cosine of 2x term. Okay, so then we just repeat the same thing with the sine term just to kind of quickly read them off. So we're going to get a C1 from here. We're going to get a plus 4C1 from here and a 4C2. So if I put all of this stuff together, I simply get, well, the C2 term is going to be my plus 4C2. And there I mean C1 from here. And my C2 term would be a that's why it's off. I made a typo up here, and I'll leave this in the video just as a learning experience. So here, I noticed the typo just because I have the solution, but in general, if I did not have the solution, this typo would lead to my final differential equation not having an issue here, but in the final answer, it wouldn't be a solution. So that's why it's important to check your solutions, and again, I'll just leave this here as a learning experience. Okay, so here with this negative fixed, this positive over here becomes a negative. And from here, then if I take this and this, I get my minus 3C2 all times sine of 2x. Okay, so now if I want this thing to be a solution, if my ansatz that this is a correct functional form for a solution is correct, then these things have to be equal to the terms up here, okay? So here, what I need to be true, so need, is for this to be exactly equal to, well, here I had a 5 times cosine of 2x, plus, on the other hand, I had a 10 sine of 2x. Okay, so this thing gives me a system of equations. So I can simply say something like, thus, my coefficients will need to satisfy the two equations, minus 3c1 minus 4c2 is equal to 5, and 4c1 minus 3c2 is equal to 10. Okay, so at this point, previously with the ansatzes, it worked out to be nice in the sense that when I got a system of equations, it was kind of always written in the form where I could just freely solve for one coefficient and do my back substitution stuff. Here, I have a legitimate problem that I have to work out to solve. So you have options. So I'll just kind of split this up. So option 1. What we could do is you could do your linear algebra thing where you rewrite this as an augmented system, 5 and 10, and you could row reduce this thing. Or you have option 2. You could do the thing where you solve one equation, back substitute, and do all of that stuff. So in this case, if I call this equation 1 and this equation 2, what you could do is something like equation 1 implies that C1 would simply be equal to, well, here I'd have 5 plus 4C2 all over negative 3. And then you would take this, so say C1 plus equation 2, and that would imply, if I take this and I plug it in here, I would simply get something like 5 plus 4C2 all over negative 3, and again, multiplied by the coefficient of 4 out front, minus 3C2 is equal to 1. So here, this is an equation that only depends on C2. So here I can say this implies, and I could solve this for C2, and when I go through to do that, I will find that C2 will simply be equal to -2, and then I take this and plug it back into the top one over here, so then I can say, thus, C1 is equal to 5 plus 4 -2 over -3. And this is just simply equal to 1. Okay, so this is one way that you can go about finding the solution. Or you can do the linear algebra thing over here where you RREF this, where once you show your work for doing that, you'll get the identity matrix here, and you'll end up with a 1 and a -2 just from the work over here. Okay, so you have your options. You can do linear algebra, show the steps for row reducing, just to make sure that you're actually solving the equation, or you can do option 2. Generally speaking, if it's a small system, I would prefer option 2 personally, and if it's a larger system, I'd go to option 1, but that's entirely up to you. Okay, so here, since I found C1 and C2, I can thus go back over here and say, hey, I now have a solution, right? So I can say the solution is now going to be simply y sub p is equal to, so C1, so just cosine of 2x, minus 2 sine of 2x. Okay, it's a good idea to check your answer at this point. Okay, so you can pretty freely check these answers just by taking the derivatives and plugging them back in. And there's a lot of steps here where things could go wrong, where you might not notice, right? So for instance, here earlier I dropped that negative. I had this to be a positive. That would mess up this system here. That will give me either no solution or a different solution, right? Those are my only two options here, since the coefficients are not 0 for each of them. Linear algebra theorem there. So in that case, I would get something that wouldn't be a solution, but since I didn't notice that error in my work, if I didn't have some way to check my work, I wouldn't have noticed it and would lose points for having kind of this negative off. Generally speaking, just if it was exactly that typo that I made here, that would probably just be -1 point or -0.5 a point for not being able to compute this derivative correctly, but then doing everything else correctly. Okay, so what's the lesson from this case? Well, the lesson here is that if I have something of this form here, then this ansatz will work, and generally the kind of open question is, will that work for all possible differential equations that have this form? So if I say change the numbers here or change the coefficients, would it still work? And the answer to that is no. So let's go look at that. Okay, so just in slide form and a comment here, I do realize that every time I've tried to put these type of things in slide form, I have to compress things and stretch it so it fits. And unfortunately, being able to kind of write everything out here, there's not really enough space, so it does get a fair bit of stretching. So I've started uploading these to learn as well. And for this lecture on, I will always include a hyperlink, probably in the This Is section, where if you just click this and open it up, it will auto link to this page here, where you can see it in better detail. And if you download this, or just do like right click save as, just saving it in kind of a random location and open these guys up. Here, it's kind of in all its glory. You can zoom in on the bitmap and get all of the little details here. So hopefully that helps with following through here. For these examples, it shouldn't be that big of a deal if this isn't easy to follow, simply because if you're wanting to read it in lecture slide form type thing, these are, for the most part, in Trench. But for the questions that aren't in Trench, or for the ones where I have details like how to solve the system that Trench doesn't contain, hopefully that will help you out there. So yeah, just use that as a new resource, and I'll keep doing that going forward. Okay, so now that we've done that example, let's look at another example. So here we want to find a particular solution of this differential equation here. So let's just set this up in Paint. Okay, so this is the thing that I want to find a particular solution of. So last time we had great luck when we made the ansatz that y sub p was just equal to some constant, say C1 times cosine of, in this case, I would want 2x plus AC2 sine of 2x. So the question is, does this ansatz work here? And if not, why doesn't it work? Well, it turns out this ansatz does not work. Just to see real quick, using the principle of linear superposition on the complementary equation, that bit is equal to 0, we would simply get second derivative of cosine of 2x here, which would be negative 4 times some arbitrary constant cosine of 2x plus 4 times arbitrary constant cosine of 2x. This bit here, this term, when I plug it into the differential equation, or the complementary bit would give me 0 is equal to 0. Similarly, if I were to take this and plug it into the complementary equation, taking two derivatives would give me a negative 4 sine of 2x with that arbitrary constant again, plus 4 arbitrary constant sine of 2x. Again, 0 is equal to 0. So this thing here will not work since y sub p solves the complementary equation y double prime plus 4y is equal to 0, right? So if I do this ansatz, I'm just going to get 0 no matter what these constants I pick are. Okay, so in kind of analogy with what we did before, we're thus going to pick a new ansatz where we multiply all this by x. So explicitly, one would just write that y sub p is equal to, and again, this is by guess, or ansatz, that y sub p is just x times arbitrary constant times my cosine of 2x term here, plus another arbitrary constant times my sine of 2x here. Okay, and close parentheses. So if I make this ansatz, let's see what happens. And in theory, what should be happening in the back of your mind is, hey, this thing worked in the previous cases when I was doing exponential terms, so it might work here. So now we're all able to compute these derivatives. So just to save a bit of time here, I'm just going to write them out real quick. So explicitly, when I take the first derivative of this and then simplify it a bit, I can rewrite it like this. Okay, so again here, I'm really just doing the product rule and then kind of drawing it out immediately. And from here, the next thing I can do is I can compute the second derivative by simply taking the derivative of this thing here, and then recall we need to use the product rule here. So if I do that and then simplify, this whole thing then becomes this expression here. Okay, so now that we have the first and second derivatives, all we have to do is take these two terms, plug them into here, and see what happens, slash see if this ansatz actually even works. Okay, so if we do that, I would want to compute my y double prime sub p plus 4 times y sub p. And we can notice something pretty immediately. This term here, this 4x with this sine cosine sum, is the same thing as this, just with the difference in sign. So this term cancels with this term. And we ultimately needed that to happen here, otherwise this ansatz wouldn't work, because I'd be stuck with for like something times x times the sums of sines and cosines, and there's really nothing like an x cosine or an x sine on the other side. So that would probably cause issues with being able to satisfy those equations. Not necessarily, but it actually works out that it would in this case. So yeah, but here, if I notice that those cancel, so that cancels with this, so all I'm going to be left with is this term here. So explicitly, this thing would simply be equal to minus 4, the C1 sine of 2x, plus this 4 C2 cosine of 2x. Okay, so if this thing is going to be a solution to the differential equation, then I need this thing to be equal to this. So we need this equality to hold. If it doesn't hold, then our ansatz, or if we can't make it hold, then our ansatz doesn't work, and we could try a different one or maybe a different method, that type of thing, but we would be out of luck for this ansatz. So we need this thing to be true. Okay, so how can we check to see whether or not we can make this thing to be true? Well, just kind of by direct comparison, you can notice I have this 8 and I have this 4c2. So if c2 satisfies the property that 8 is equal to 4c2, then we can satisfy that term, and we have this minus 4c1 times the sine term is 12 times the sine term. So if that equation can be satisfied, then we're good. So if we put this together, we can formally write this as a system of equations as follows. Minus 4c1 better be equal to 12, and my 4c2 better be equal to 8. Okay, so this system is very trivial to solve, right? So just dividing by 4 gives me immediately that the c1 has to be equal to -3. So c1 is -3. And over here, the c2 tells me that c2 has to be equal to 2. Okay, so my ansatz worked. I found a thing that solves the equation. So now what I simply do is just plug them into my ansatz, and I can say, thus, y sub p is equal to, so we had that x on the outside, minus 3 times the cosine of 2x plus 2 times the sine of 2x. Okay, so that is our proposed final answer. It's always a good idea to go back and differentiate this and make sure it does actually solve the particular, the forced equation up here, but it actually does in this case. Okay, so if I just kind of put this back, we've kind of noticed so far we have two cases. If this thing is not a solution to the complementary equation, then we can just simply assume that it's some sum of sines and cosines with arbitrary coefficients in front of those two terms. And on the other hand, if this sine of 2x and cosine of 2x term end up solving this function here, then we need to make this other ansatz where we take x times the sum of the sines and cosines. So in general, up to this point, if we want to try to solve these types of equations, we first need to find the complementary equation, or the solutions to the complementary equation, or simply kind of make a guess and see if it works. If it doesn't work, then we kind of make an estimated guess, or educated guess, for what would be the correct ansatz to use. Let's look at another example where instead of having just a constant in my equation, so instead of having some constant times cosine, I have a polynomial. Okay, so just in slide form, and I will put that hyperlink before I upload it. I'm just going to batch do it, so it takes a little bit less time on my end. Let's look at this equation here and try to find a particular solution of it. Okay, so in this case, if I were to try to make the ansatz that y sub p was simply that sine and cosine thing, so some constant times sine of x plus some constant times cosine of x, what would end up happening is, at the end of the day, when I differentiate all of these terms here, this thing would become something that would look like some constant times sine of x. So let me just put my constants in here real quick. So some new thing, we'll just call it f of c1 and c2, sine of x plus another function, say g of c1 and c2 of cosine of x. And I realize this is messy, but just kind of demonstrating a quick point. But if I differentiate this term, or this function, then here I'm just going to get sines and cosines. Here I'll get sines and cosines with different coefficients in front of it. So I'll end up with something like this, where if the sine of x and cosine of x satisfy this difference equation, this could be 0. But if I try to make this thing equal to these expressions here, I run into a problem because this thing does not depend on something that looks like x cosine of x, right? There's nothing that would look like this and here. Thus, the previous ansatz we used can't work here, just purely based off the fact that if I do this, I can't match the x coefficient. So I need to pick a different ansatz. So what's the ansatz that I should pick? The big open question here. Well, it turns out that since my issue there was that I did not have a x term in my final left-hand side of the equation, what I could do is simply assume that I'll have some x term. So I could write something like a naught plus a naught x times my cosine of x. So that gives me an x term here. And you might think that it would be fine just to assume that the x coefficient for the sine of x should just trivially be 0, because, I mean, there is none over here, right? Like, yeah. So it turns out that that's in general not the case. And if you want to really see why, you can just make a simplified ansatz here, and you'll notice that you can't actually get a solution. Okay, so I do actually need this term here to be able to make this thing work, right? So it's really that these two polynomials are kind of working in harmony in some sense to be able to match the forcing term. Okay, so under this ansatz, so if I make this guess, then I compute my first and second derivatives. So just doing that real quick. And taking the second derivative and simplifying it out simplifies to this nice expression here. Okay, so now that I have that simplified as these two terms here, I do my standard trick where I now want to examine the left-hand side. So I simply want to examine this expression here. Okay, so if I do this algebra for y sub p sitting in here, what does this thing simplify to? Well, it's a little bit ugly, but once all the smoke clears and you capture the cosine terms together, the cosine terms would give me simply this expression here. And the sine terms simplify to this expression. So it's a bit more messier than previously, but it's still basically the same idea. Okay, so now if this ansatz is going to actually give me a solution, then I need to have what? Well, this needs to be equal to the forcing term. So this thing better simplify to 16 plus 20x times my cosine term plus 10 sine of x. So I need this thing to be true, and here I can simply set coefficients together, right? So this thing here and the thing that I need it to be equal to have the same functional form since I picked a valid ansatz. Therefore, I can just set the coefficients of everything equal to each other. So from here, I could rewrite this as a system of equations. Okay, so something that we would see from linear algebra. Okay, so let's see what we get. Well, here the 16 needs to be equal to the constant term up here. So here I get a naught plus 3a1 plus 3b naught plus 2b1 all needs to be equal to 16. Next up, setting this one, I get 20 better be equal to a1 plus my b1. Here, slight typo, needs to be 3b1. So do remember, typos happen, dropping constants happen. Be very conscious of doing that because there really is no way to check whether or not this will work until you get the final answer and plug it back in. So keep an eye out for things like that. Again, an error like this, given that everything worked kind of going forward, would probably just get you like half a point to 1 mark off if you did everything correctly. Okay, so going forward from here, the next equation would be setting this 10 equal to the coefficients here. So here I would get equals 10, and setting the sine coefficients would simply give me, here I'd have a b naught. Here I'd have a plus 3b1. Here I'd have a minus 3a0. And here I'd have a minus 2a0, or a1. Okay, so that would be my system of equations for this bit. And for the last bit, I simply have 0 because there's no coefficient of x sine x. And that would simply need to be equal to b1. And here I get minus 3a1. Okay, so here I now have something that you would have seen in a linear algebra class, and our goal is to solve it. So you can kind of note something that can be useful. These two equations that I'm underlying here form a system of equations that are separate from the rest of the equations, right? I can solve yellow together at the same time to find A1 and B1, right? So just keep an eye out for little tricks like that. So here I can simply say something like, put a yellow box here, solving for this thing gives me simply what? Well, here I get A1 is equal to, actually it's easier for this one, I get, say, B1 is equal to 3A1. I could plug it in, isolate for A1, and then plug in here. Okay, so suppressing those details, here I simply get that A1 is equal to 2, and B1 is simply equal to 6. Okay, so having this now makes it easier to solve the rest of the stuff. So let's just underline it. And now I can say something like, thus the blue stuff becomes, well, what would the new system be? If I plug A is 2 and or A1 is 2 and B1 is 6 into here, this top equation would simply become, well, I would get my A0 that's still kind of stuck around, plus my 3B0, and then this would be 16 minus 2 times 3 minus 2 times 6. So if you do that arithmetic, this would be minus 2. And then from here, doing the same thing here, I would have my A0 and B0 terms surviving. So I'd get this plus, and here I dropped a plus sign. B0 is equal to, well, it would be 10 plus 2 times 2 minus 3 times 6. So if you put all that together, that's just minus 4. And again, this is an easy problem here to solve. So in this case, I would simply get A0 is equal to 1, and B0 would simply be equal to minus 1. Okay, so here, what I want you to do when attacking these type of problems is once you get to the system of equations, be kind of very careful with how you choose to do it. You could solve this as a system of 4 equations and 4 unknowns, but they're kind of decoupled. And generally speaking, for these type questions, you'll always have some degree of decoupling. So just keep an eye out for that. Okay, so what I've done now at the end of the day, I've found my coefficients here and my coefficients here. So I could just put these into this expression here for y sub p. And if I do that, I simply say, thus, y sub p is equal to, well, 1, and my coefficient for this bit was 2, so it's this first bit here, minus, or sorry, I'll just make it to a plus, 6x minus 1 sine of x. Okay, and this thing is going to be a solution. So we'll say solves the DE. Okay, so there was that example, and you can notice that this ansatz works, and you could further kind of notice that cosine wouldn't actually solve this differential equation here, right? Or neither would this sine term. Therefore, I didn't need to do that thing where I multiplied by the extra factor of x, and this ansatz actually worked. So now I'm going to suppress the details of this example just to try to keep things a little bit minimal. But here, if we look at this example, in this case, cosine does solve this equation, right? If I took cosine of x, took 2 derivatives, I get negative cosine of x. Those would cancel to solve the complementary equation. And the same thing for sine of x. So if I make the same ansatz that I made over here, namely this ansatz that I had this polynomial cos x plus polynomial sine x, that would fail to solve this differential equation. And the reason why is at the end of the day, once I plug things into here, the fact that sine and cosine solve this equation would make the constant terms go away. Just like what we saw in the previous lectures where I did exponential forcing terms. Okay, so I'm not going to cover this example here, but definitely see 5.5.4 in Trinch if you want to see how this works. But TLDR, since this thing is a solution and this thing is a solution, you have to assume an ansatz of the form polynomial, second degree polynomial with a constant term being 0. And hopefully at this point it should be pretty clear why you would need to do that ansatz. And in practice, if you ever make the wrong ansatz, you'll pretty quickly see that it doesn't fit. Okay, so let's talk about a kind of summary of what we have so far in the form of a theorem. Okay, so suppose omega is a positive number, and it could be negative, it doesn't have to be positive, but it's traditional to do this, and let p and q just be some polynomials. And then further, we're going to let k be the larger of the degrees of p and q. Then this equation here has a particular solution given by this expression of this form here, where these polynomials are standard polynomials with these constant terms here, provided that the sine terms and cosine terms are not solutions to the complementary equation. So generally speaking, you only need to check one of these, because if sine of omega x is, then cosine of omega x is, and vice versa. So that really just comes from the previous work that we did with solving these differential equations. In that third case where we had a complex roots, well, complementary pairs of complex roots. If one solves it, the other one has to as well. Okay, so now that begs the question, what do we do if these things are solutions of the complementary equation? Well, if these things are going to be solutions to the complementary equation, then the differential equation over here can be written in a particular form, right? It has to be able to be written in this form here. Why? Well, if this cosine of omega x is a solution to this, then I know that omega is one of the roots of the characteristic polynomial. And for omega to be one of the roots of the characteristic polynomial, it has to have the form some constant times r squared plus omega squared r, right? Where the constant's on the outside of the polynomial. Thus, I have that if this thing's a solution, the left-hand side has to be of this form, okay? And if I'm in this case, then all I have to do is multiply these expressions by x, and I get the same type of solution that I had before, okay? So that's all this is saying here, is if these things are solutions, then y sub p is still my solution, like the ansatz I need to make, but these polynomials need to be scaled by x, okay? Pretty straightforward here. In practice, the way that I generally approach these type questions is to first just assume that my particular solution is the form u, where u is a particular polynomial, times cosine of omega x, plus, say, u2 times sine of omega x. Chase through all the details, get a nice differential equation for my u and my u prime, and then just plug in the fact that I know that they'll have to be different polynomials to be able to solve for things there. That just makes this process that I've done a few times of computing these derivatives a little bit cleaner, right? I don't have to deal with this kind of complex mixed match stuff happening. Okay, and yeah, it's kind of your choice if you want to do that or the arbitrary function u, but at the end of the day, you do need to use the method of undetermined coefficients, namely making the ansatz that you get these polynomials somewhere. Whether you do it at the beginning or whether you do it after you get your differential equation is kind of up to you and the framework that you want to do the problem in. Okay, so now that we have this, I want to make one more comment. In your text, there's this theorem 5.5.2. So just to show it over here, we have this theorem here. And what this theorem is really just saying is, hey, if you make an ansatz that y sub p is of this form, where these are polynomials with these particular coefficients, then the polynomials multiplying sine in these various derivatives can be obtained just by simply replacing these coefficients here with these coefficients and those ones with these ones in the various polynomials for cosine. Okay, so basically what this is doing is when you go to chase all these details, you'll have some stuff with sine and some stuff with cosine. This is telling you that there's a relation between that stuff. So you can use this to check your work. I would not memorize this, though. Like I would do the things manually because you're more likely to make a mistake when you try to memorize them. Yeah. And further, if you just memorize it, if you made a mistake when, say, finding the polynomials for cosine of omega x, if you use this method, then that mistake's carrying over to the sine bit too, right? So it doesn't really help decrease errors when, say, computing the sine term, but it lets you verify that you didn't make errors, or very likely didn't make errors. Okay, so let's look at another example. Suppose I asked you to find a particular solution of this form, or for this differential equation here. So the key thing to notice for this question is that I have both the cosine term here and this e to the minus 2x term, and they're multiplied by each other. So this is really working with the general form that I mentioned in the first slide of this lecture. Okay, so if I wanted to tackle this, we have a few kind of different ways we can go at it about now. So if this cosine stuff wasn't here, then I would have made the ansatz y sub p is equal to u e to the minus 2x, where u is going to be a polynomial whose form and order will depend on whether or not e to the negative x solves the complementary equation, or x e to the negative 2x solves the complementary equation. So negative 2x for the power in both cases. Okay, so we know how to handle those cases. Now, if we did not have the cosine and sine terms, or sorry, if we did not have this e to the minus 2x term, then we could make the ansatz that y sub p is equal to some polynomials, say a of x cos of 3x plus some b of x sine of 3x. Okay, so if I didn't have that, I would make this ansatz here, where these terms a and b would depend on whether or not this cosine of 3x solves the differential equation slash the sine of 3x solves the complementary equation. Okay, so here we have these kind of two ansatzes that work in these two different cases. It turns out that if you wanted to get something that's a solution in general, you'll always want to assume that y sub p will be of the form e to the minus 2x times these polynomials, which I'll call it a1 of x and b1 of x, so this thing here, like that, that this would be the proper ansatz here. So now the values that you explicitly would put here would depend on whether or not this e to the minus 2x works as a solution, and whether or not these cosine of 3x and sine of 3x work as a solution. And again, that's all to the complementary equation there. So I could do this monstrosity of an ansatz here to solve this problem, but that's problematic for a few reasons. One, when I go to compute my derivatives, say y prime p, I have to use the product rule 3 times because I have this times this times this. That gets messy really quick. So just to clean things up a bit and to avoid having to compute derivatives of this and then its derivative after that, what we're going to instead do is basically apply this method for u, get a differential equation with respect to u, and then we're going to assume that that u has a particular solution, or that differential equation for u has a particular solution that's of this form where we know what a and b have to look like based off of whether or not the cosine terms solve a differential equation. Okay, so we're going to kind of split this up into two cases instead of assuming this beast of an ansatz, which you can assume this if you really want to, and it does work. It's just, as a human, you don't really want to do that, but maybe as a computer, you could code it to do that. Okay, so with that preamble aside, let's go and try to do this. So we're going to make the ansatz that y sub p is going to be equal to u e to the minus 2x. 2x. Okay, so here we could already guess of what the form of u needed to be from kind of our previous work, but here we're just going to let u be arbitrary. Okay, so if I put this into the differential equation, so using this in the differential equation gives, well, I'm just going to do these computations. We've done these similar type computations before, but let's see what things end up turning into. Well, after all the smoke clears, this is what I get. And notice that the right-hand side, the only change is that I no longer have this e to the 2x. So what's really happening when I make this ansatz again is that every term here will have an e to the 2x term, so then I can just cancel the e's to the 2x's. Okay? So again, if you're doing this in like homework, you should analytically compute this out to simplify this equation to show your work here. But for the lack of time and the fact that we've done similar computations before, I'm going to skip the details here. Okay, so now this thing is of the form of something I've already solved before. Okay, so we've solved things like this with the sines and cosines just in the last 4 examples, right? So here I can apply that theorem, and I can note that since, or as, my sine of 3x and my cosine of 3x do not solve the equation u double prime minus 7u prime plus 12u is equal to 0, so the complementary equation, then I can make my ansatz of the form as follows. So we let this u sub p be equal to, well, in this case, this would just be of the form, say, a naught plus a1 x cosine of 3x. And again, I want this polynomial here because the highest order of these polynomials is 1, plus an arbitrary polynomial for, or arbitrary first order polynomial for sine times sine of 3x. Okay, so again, this is my ansatz. I'm assuming I can find a solution of this form, and I know I can by our previous work, or if you want to be more formally, that theorem that I mentioned without proof. Okay, so that's my ansatz. So then what we do is exactly what we did before. We take this ansatz and plug it into the equation for u. So now we're going to take this and plug it into here. So explicitly, using the yellow and the green gives, and for your homework, you'd want to show the work for computing these derivatives. Maybe use that theorem 5.5.2 to verify that your work is correct before going forward and having errors propagate. And then you'd want to show what happens when you plug it in here and simplify. But just for lack of time, I'm just going to write it out. So this thing would simply give this new equation that u sub p prime prime minus 7u sub p prime plus 12u sub p is simply going to be equal to, well, when the smoke clears, I'm just going to get this thing here. And again, here in the process of doing your computations, it could be useful to first call this thing here some polynomial, say p1, and this thing here some polynomial called p2. Write out the left-hand side in terms of p1 and p2, and then simply use the fact that those are going to have to be polynomials of these forms to compute the stuff here. Okay, so now what's next? Well, this is the left-hand side of the differential equation. So if this is going to be solution, I need this thing to be equal to the right-hand side of the differential equation. So if I just go back up here, this is what the right-hand side of my differential equation was. So I can take this guy and paste it here. I need this equality to hold. So what I then do at this point is I set up a system of equations, and I can just simply write, or, well, if these things are going to be equal, I'm going to have 2 needs to be equal to the stuff of the constant term here. So explicitly, I'd have 2 needs to be equal to, here I'll have my 3a naught again, here I'll have my minus 21, b naught minus 7a1 plus 6b1. Okay, and then I need the x terms to be equal, so I need 0 to be equal to, well, here I'm just going to have a 3a1 and a minus 21b1. Then working on the sine terms, so the sine term right here has a coefficient of negative 34, so I could just do minus 34. That needs to be the constant term. So just rewriting this as a system, I get this plus 3b naught minus 6. And again, I'm rewriting it of this form just because I have a system of equations. And ultimately, for the system of equations, as they get really bad, I'm going to need to use matrices to solve these. For this course, we won't give you a problem that's explicitly hard just for hardness sake. So you probably won't need to deal with actually using a matrix to solve a system. But in general, you will need to use linear algebra to solve these. Okay? Like real world problems, if this is say like a 30th order polynomial, you're not doing that manually. You're doing that via computer solving linear systems. Okay, so from here I want to solve this. So I use the same trick that I did before, where I would solve this equation, or put it over here, where I'd solve this equation along with this equation, and then I'd use those solutions into the other terms. That helps me avoid having to deal with this 4x4 system, and I deal with two 2x2 systems, which are much nicer. So when I solve this, so solving gives, I'll end up finding first that a1 is equal to 7 and b1 is equal to 1. And after I do that, I will find that a naught is just going to be equal to 1 and b naught is just going to be equal to minus 2. Okay, and again, that's solving one and then the other. I highly recommend doing it like that. But if you really want to solve the 4x4 system, you can. It's just kind of up to you there. Okay, so now from here, we can say thus, well, my y, or my u sub p, would need to be the thing that I made the ansatz of up here, so this thing here, where I have those coefficients. So just reusing some of the text here, this would simply be this expression here, where I replace these terms. So a naught is 1, so just deleting these guys here. A naught was 1, so I put it in. A1 was 7, so I put it here. B naught was minus 2, and B1 is 1. So again, notice, even though in here I don't have a polynomial sitting here multiplied by cosine, I do need it in my final answer. So if I did not include that term, I would get a system of equations that has no solution. Again, good example would be to practice that and see what happens. Okay, so now that I have the solution for u sub p, I can now plug it into my original ansatz over here, and I could simply conclude that and y sub p is equal to this thing. So let's just copy it. This whole thing that I found here, and put parentheses around it. This would then be multiplied by my e to the negative 2x. So here I could put my big square brackets to make it clear that how the brackets are working here, e to the minus 2x. Okay, so that's all there is to this. Pretty straightforward, just lots of little details, and it's kind of keeping track of your ansatzes and which ansatz you should make within which type of problem. In general, if you pick the wrong ansatz, you won't find a solution, and that's perfectly fine. It just means that ansatz doesn't work, and you need to go back to the drawing board. Okay, so the final example that I will discuss briefly but not go over is going to be this guy here. Okay, so in this equation, notice I still have this e to the negative x going on with a kind of a functional form that's similar to what we saw before. Here, I would want to apply the technique that I just did over here to be able to solve this. So again, you could make an ansatz that it's of the particular form e to the negative x polynomial cos of 2x plus another polynomial sine of 2x, and try to chase that out and find the functional forms of the polynomials as you go. but I do highly suggest just starting with the ansatz that y is u times e to the negative x, plug that in, get a new equation, and then use that theorem 5.5.1 to guess the functional form of the polynomials. So in here, just going through the stuff in Trench, we can first notice that this e to the x cosine of 2x doesn't actually solve the complementary equation, but despite that, once I use this ansatz and get an equation for u, these cosine terms do satisfy the complementary equation. So that's kind of interesting. So that kind of tells us that we can't guess the particular form of these polynomials directly based off of what or whether or not this e to the negative x cosine of 2x, and same thing for the sine term, solve the complementary equation, but we do in fact need to kind of make this guess here first, right? There are ways that you can kind of avoid going around it. They're just not really computationally worthwhile. Okay, so then after we make this ansatz here, we simply plug it in, get an equation for u, and now we can make our ansatz based off the fact that this solves the complementary equation, and our ansatz would simply be this thing here, since these are linear polynomials and I need the x because it's a solution. And now I just do the standard trick, plug this in, get a kind of ugly system of equations, which isn't too bad in this case, solve this system of equations, plug it in to find up, and then finally find y sub p. Okay, so that's our big broad overview, and if you want to see the details, again, just look in the textbook at that question in Trench. Okay, since we've gone over time, and I apologize for that, let's just jump into our assigned reading. I want you to read section 5.5. In particular, understand the different cases and why you make different ansatz in the different cases. If you make the wrong ansatz on homework, it's perfectly fine. You'll just get something that doesn't work, and then you'll go, oh, that didn't work, and now I need to pick the right ansatz. Okay? So just be careful of ansatz doesn't work versus you made a typo somewhere when writing things out. So be very diligent with watching things like that. Okay, for practice problems, I want you to look at questions 1 through 17 and 22 through 32 on this page, or these pages. Again, don't have to look at all of them, and here's your meme. How it feels when your ansatz works. Yes, it worked. We have a nice solution. And yeah, that's what ansatzes are for. Guess the solution. Hopefully it works and you find it. If not, doesn't work, try a different one. Okay, so I will see you all in the next lecture and talk to you later.